Hi, welcome back. In this lecture I will describe the derivation of a higher order finite difference stencil. So far we have been looking at first order, second order finite difference scheme, and in this lecture I would like to describe a general methodology to derive higher order schemes. So the procedure that I'm going to show in this lecture will allow us to derive a finite difference stencil for the approximation of a given derivative operator. In addition, the procedure will allow for a rather arbitrary number of grid points to be involved in the finite difference stencil. We will see that higher order scheme corresponds to take a larger number of grid points that are involved in the calculation of the approximation. This larger number of grid points yields to a leading error term that decays faster as the grid is refined. That's why they're called higher order schemes. The error will decrease faster. However, the larger number of grid points also implies that there will be a larger number of floating point operations, and this will lead to a larger rounding error. As in the previous lecture, as I told you before, the basic building blocks of deriving finite difference schemes is the Taylor expansion. So we take a function and then we derive an approximation of the values of derivative at the point x by expanding a function with the Taylor expansion. So the function will be in this case x plus delta, and we will expand the function around the point x. We can use the Taylor expansion. So far what we did, we basically neglect all these terms here. They're basically after the f prime terms. So we need to decide when to cut down our expansion. Typically in the previous lecture we cut it down here. In the current lecture we are going to take this second order derivative and third order derivative to derive these higher order schemes. So we're going to look at in this lecture is the derivation of a 4 points stencil. That means that for the calculation of our derivative we are going to take into account 4 points. So we intend to derive a finite difference stencil that resembles the one cell finite difference approximation that we saw in the previous lecture. So still we want to have our scheme to be centered. We also want to include one additional grid point on each side of the lowest order stencil. So in the case we have 2 points, we are going to add other 2 points and include this point in the calculation of the derivative. So for this reason, we will consider an approximation to the first order derivative that involves the 4 grid points. We will have h half minus h half, and then we will have minus 3 over 2h and plus 3 over 2h. So for the total of 4 points. The basic technique, as I told you before, is still the Taylor expansion, and to derive this higher order scheme, we use the Taylor expansion along 4 points. So we expand our function in 4 points. So here on this slide you find the Taylor expansion for the function around the 4 points. So we have the 2 middle points and then 2 other side. So this is the expression that we get from the Taylor expansion. The first step of our derivation is to introduce 4 unknowns called A. So we will introduce 4 coefficients for each of the 4 points involved in the stencil for the calculation of the higher order derivative. So this coefficient will be used in the finite difference approximation. So let's do this first step. So we will have here our 4 points. We will then sum it up, and each of these 4 points will have an associated coefficient. The next step is going to introduce the approximation from the Taylor expansion we derived in the previous slide. So we have this approximation for the 4 points, and then we keep all the terms up to the third derivative. Once we have that, then we collect the coefficient for fx, f prime x, f second f, and the third derivative of fx. So we will have 4 coefficients multiplying the derivative of f and f itself. So these will be 4 coefficients. What we want to do now is actually to extract a way to calculate the first order derivative. So what we're going to do is to ensure that the This term is going to be equal to 0. This term here is the one that we want to calculate. So we will put an equation that this coefficient here must be equal to 1 because we want have an approximation of f prime. We also want not to have any term coming from the second order derivative and the third order derivative. So we will set it up, this coefficient here to 0 and this coefficient equal to 0. So just to summarize, we will put this value equal to 0, this value here equal to 1 because we want to keep the evaluation of the first order derivative, and then we will make 0 this coefficient here and this coefficient here. So we then can solve the linear system by imposing this condition 0, 1, 0, 0, and we can derive the following coefficient for our first order derivative. So by using this coefficient, then we can formulate our higher order derivative. So we will have a stencil that is like the following involved this point. Without a loss of generality, we can actually center this expression, and you will see that the calculation of the derivative at the center point will be a combination of the values that are on the side multiplied by minus 27 and plus 27, and other two terms that are the next values of the function on the stencil. And of course also the grid spacing that we evaluating our higher order derivative is also larger, so in this case is 24h. We are going to use the technique that we've been using to analyze the numerical properties of first order derivatives. Those were of second order, also in this particular case. So we can exactly use the same technique. So given this higher order approximation of the first order derivative, we perform the analysis with the complex exponential. So we are going to take our expression, and then we're going to replace with the exponential of complex values, and then we are going to do again Taylor expansion. So if you are doing exactly the same operation we did in the previous lecture, we substitute with the exponential. We found this expression here. This expression here can actually then compress in a small expression that is the following here. So what the important point here, one thing we can do is to make a Taylor expansion of this cosine square and sine in the same way we did in the previous lecture, and find what is the leading error. So you will see that the numerical way number, again, we find that the leading term here is equal to k. This is correct, and this is actually the error. So the important point here is that error is of the power of 4 of h, right? So the error is not quadratic, is to the power of 4. So this has a leading error term that is proportional to h to the 4th. So this means that the reduction of the set size h by a factor of 2 reduces the error of the wave number by a factor of 16, right? That's the meaning of having an error that scale as the 4th power of h. So what are the disadvantages of higher order approximation? So we saw that is very convenient because the error decreases very fast. However, also have some issues. Well, the first, probably most important issue with the higher order approximation is how to handle boundary condition. We saw that higher order approximation, they require a quite larger number of stencil points, right? So the point is that at the boundary, we don't have often too many points where we can include our boundary condition. We saw that for the lowest order approximation stencil that are located closest to the boundary, the outermost points at the stencil do not normally extend beyond the boundary, but instead they would be located on the boundary, which makes it possible to incorporate information from the boundary condition in a natural manner. So for the lower order approximation, where we just need 1 point, to put boundary condition is quite easy. However, for a higher order finite difference stencil, such a situation would imply that some points of the stencil are located outside the computational domain. So a common solution to this problem is to use the lowest order stencil in the very vicinity of the boundary combination with the higher order stencil applied in internal grid points. So how this is going to work? So we have an internal point where we can have larger stencil. For instance, we can have a stencil with the fair grid points. However, when we need to put the boundary condition on the boundary, we cannot have a larger stencil because we don't have many points outside the domain. So for the boundary condition, we typically use a lower order approximation of our derivative. So we mix it up, lower order approximation at the boundary and higher order approximation in the internal point of the domain. However, this leads to mixing different orders numerical scheme for the boundary condition. And this also means that the error analysis that we have been doing by using complex exponential becomes more difficult. Also, the order of convergence is reduced since it's determined by the purest approximation present in the numerical scheme. It might be that we are using higher order scheme in the domain, lower order scheme at the boundary, and the total order of the scheme is actually quite low because it's determined by the scheme that we use at the boundary. So we see in the third module of this course that the better solution is to use higher order finite element methods. So not finite differences, but finite element methods that match much better with the boundary that we have been given. So we can exploit higher order approximation also in the very vicinity of the boundary. In addition, the boundary can be curved. It does not have to coincide with the Cartesian coordinate axis. We will see this in the third module of this course. So this was the last slide of my presentation. In the next lecture, we're going to look at eigenvalues problem in SEM. Talk to you soon.